Thanks everybody for coming. Welcome. It's finally time we get to talk about some PDSE this week. So this should be fun. So this is Performance Basics, and again, I'm Tom Reed with IBM DFS Level 2 for PDSE support, also RLS on the side. I've been with IBM and working on PDSE for just about 10 years now, which has been a lot of fun. This is Jim's favorite slide. Hoopla! Again, Cher has set a really ambitious goal for evaluations, so please fill out your evaluations after this. The evaluations help get us here and let us know what you guys want to hear about. Now on to PDSE. So we're going to be talking about two main aspects of PDSE performance in this presentation. We're going to talk about performance from the SYSPLEX and system level, and we're going to talk about performance from the dataset level. First though, in all these presentations, I like to do a quick level set just for folks who don't necessarily have much PDSE experience. So we'll start with the lowest of the levels, the acronym. PDSE stands for Partition Dataset Extended. And what a PDSE really is it's a homogeneous collection of 4K pages on Datasets. We have two potentially PDSE address spaces. We call them SMS PDSE, SMS PDSE 1. And those two address spaces are what serve client access requests for PDSE members. In the background, those address spaces are also what handles serialization, buffering, and all the other under the covers action that goes on with PDSE. So these are the four aspects of system and SYSPLEX level performance that we're going to talk about for PDSE. We're going to talk about sharing, features, workload, and caching, and how those all impact PDSE's performance within your environment. Again, we want to make sure we have our terminology straight before we dive into this discussion. So you guys all know your general open types. We have open for input, commonly known as read. We have open for output, which we commonly know as write. Now, when discussing PDSE, we need to understand that when we're doing an open for output and we're going to write something, we use this for a whole variety of actions. We do it to create members, to rename members, to delete members, or replace members. And notice that I didn't say that we use it to update members. And that's because for PDSE, when you write a member out, when you change something within your member and then save it, we don't actually update it in place unless you specifically want to do that. Instead, what we do is write a whole new member out and then unchain the old version from our internal indexes, and that's pretty important. We'll see a bit about that later. Finally, we do have an open for update, and that's what we call update in place. And for PDSE, update in place is actually very rare. So we almost never use it or have to deal with it, but it does have some performance impacts in that it's going to stop basically all the other action in the PDSE. Finally, we want to talk about our two serialization methods. We have GRS, so Global Resource Serialization, and XCF, which is Cross-System Coupling Facility Messaging. And these are the two ways that we mediate serialization for PDSE within your SYSPLEX. When we talk about serialization, we have three constructs for PDSE that work with various aspects of our serialization. We have latches, and we use those to serialize our internal structures, which really means control blocks. This is how we keep things inside the address space serialized correctly. We have NQs, and we actually only use a couple, I might call them raw NQs for PDSE. We use those to serialize some of our dataset functions and also to determine some of the sharing modes, but we rarely just use an NQ alone. We also have locks, which are kind of a composite structure. Locks are what we use to provide serialization at the dataset level. So this is sysplex wide. And those are actually composites of NQ-like structures. And we're not going to talk about those in depth in this presentation, but again, just remember that that's how we serialize at the data set level. So now on to our sharing modes. And hopefully this graphic makes clear which one of these I prefer, and you should be preferring in your shop. We have extended mode sharing. We've had this since about 1.6, I believe it was. It's been around a long time. This is the newest and preferred sharing mode. To enable extended mode sharing in our IGD SMS ParmLab member, we just specify PDSE sharing extended. And this is going to give us sharing at the member level between systems within your sysplex. And remember that terminology because we're going to see the difference between these two in just a second. It's important to note that extended mode sharing uses both XCF and GRS to mediate sharing, and because of that, it means that extended mode sharing is strictly limited to the sysplex scope, so a single sysplex. Sharing between sysplexes with PDSEs in extended mode is not recommended. Normal mode sharing is actually the original mode of sharing that PDSE shipped with. It's also the default mode, so if you don't specify anything in your IGD SMS, you will get normal mode. You can also, if you want to be explicit, go ahead and specify it on your PDSE sharing parameter. And it only supports dataset level sharing between systems, but you can share at the member level within a single system, and we'll talk about that in a moment. Normal mode sharing, though, only uses GRS for serialization, and that does have, well, I was going to say some advantages, but no, it only has one advantage. So when we're in normal sharing mode, our PDSE datasets can be locked either as only readers, so basically the equivalent of shared, or exclusive by each particular system. So when we're locked shared, that system can do any input operation, so any read operation, but no output operations. This is pretty normal stuff. When the system has it locked exclusive, and remember it's locked at the system level, so on behalf of a particular system, and that particular system can do any input or output operation, but it's going to prevent any other access from outside that system. And what this leads to is it means that that system that's holding that data set exclusive is going to block access from any other PDSE that wants to use that. So this can have a major impact on your throughput if, for instance, you have one system that's doing a lot of writes, but other systems want to be doing reads to it, for instance. So if that is not compatible with your workload, you could see some big issues in terms of performance. The one advantage to normal mode sharing, though, we wouldn't keep it around if it had none, is that it allows for sharing between sysplexes, so long as those sysplexes are within the same GRS plex. And again, that's because it only uses GRS for serialization mediation. So this is just a quick example. We can see here that system A has done an open for output, and it's been granted the exclusive lock on our PDSE over here on the shared DASD. So that PDSE now has a global lock state of exclusive. It's locked exclusive by system A. So when tasks on systems B and C here come in, either for an open for output or an open for input, they're going to receive these IEC 143I messages, specifically the 213-70. There's a whole table of exactly what these mean in the PDSE usage guide. But these two systems are being blocked by system A. And so as long as system A is sitting on that exclusive lock, system B and C are going to be made to wait. So this guy's supposed to be going really fast. He's not just, having a bad day or something. So we're moving on now to extended mode sharing. As I mentioned, this is the newest and preferred sharing mode. This is what we should all strive to be using in our environments. And the major advantage is that it fixes that one huge downside of normal mode. We can get multiple systems to have the data set open for both input or output all at the same time. So we can share at both the data set level and at the member level between systems. The only case where opens would be blocked is where an update is occurring to a member and we can't access a member where an update in place is going on. That would cause data integrity issues. We can't write and read from the same member at the same time. So here's another diagram. Essentially what you should take away from this is that systems A, B, and C are now all playing nicely with the same PDSE, and notice that they're actually open to particular members because we can share at the member level. So if you guys have been attending my sessions or been using PDSE for a long time, you may already be running in extended mode, and so this may be a little boring, and you're saying, why do I need to think about this again? We've already thought about this. We had meetings about this. The two major drivers of sharing mode discussion right now are changes to one's code promotion or code migration process within your environment, and specifically this seems to be driven due to the PDSE requirement for COBOL 5 and onwards. For those who don't know, COBOL 5 and onwards requires program objects. Program objects need to reside in a PDSE data set. And a lot of shops were keeping their load modules in a PDS, and we're using that, we're sharing that rather, between their test and production SYSPLEXs. When you go to a PDSE and are running extended mode sharing, that's not going to work. And that's because extended mode sharing has a strict scope of a single SYSPLEX. So you risk losing serialization on your PDSE if you're trying to share between SYSPLEXs. This can result in corruption, can result in hangs, other issues, and as you can imagine, you don't want that to be happening on your production SYSPLEX when you're just trying to do code promotion. So this is a driver of discussion for sharing modes again. Yes?
Are there GRS-ONL recommendations specifically for PDSE?
Are there GRS, excuse me?
GRS-ONL?
PDSE uses RNL no. So it, everything is systems. Okay.
Specific.
Nope. It's actually, it's very simple in that. Okay, excuse me. So we're gonna go ahead and move on to features that can impact your performance at the system and SYSPLEX level. And really there's only one that we need to worry about. There aren't that many buttons or levers for PDSE. And that is buffer beyond close. Buffer beyond close is really exactly what it sounds like. We hold on to our index buffers beyond the last close of a PDSE data set. We can set this up using our IGD SMS parameters, and note that this needs to be set up separately for both the PDSE and PDSE1 address spaces. You can actually run one with buffer beyond close, one without, switch them around, run both, run neither. It doesn't matter to PDSE. In all honesty, PDSE address spaces treat each other as different systems, so they're essentially entirely independent anyways. So our settings here can work in any combination. So by holding on to these buffers beyond close, this can help your performance in particular use cases where you're doing last close of a data set and then reopening it almost immediately. And by almost immediately, I mean within about 15 minutes. If you're using our standard LRU processing timing, pages stay in cache about 15 minutes, depending on how heavily the cache is being used. So if those pages are still there, buffer beyond close can make it so we don't have to go back out to DASD to read your index pages. We just grab them back from cache, and you're set to go. The downside of this, of course, is that we have to hold on to those buffered pages. If we're not getting rid of them and enabling them to be reused, we need to store them somewhere. And so this can marginally increase your storage usage. And there are some cases, we have a particular APAR here, OA47035, that I highly recommend you have on. It's not that new of an APAR anymore, so hopefully everyone's caught up. But if you're not, grab that, especially if you're doing a lot of decollect activity to volumes with PDSE data sets. And that's because decollect essentially just goes through and touches every PDSE data set really quick, looks at whatever statistics it needs to. But for each one of those PDSEs that decollect touches, we need to actually do an open. We load 5 pages into storage. This isn't a big deal if you have 100 or 1,000 PDSEs in that decollect. If you have 100,000 or 200,000, those pages start to add up, and that is storage usage. And because if you're running with buffer beyond close, you'll go ahead and hold on to those pages longer than you normally would. So what this APAR does, it essentially says if the open's coming in from decollect, even if buffer beyond close is on, don't worry about it. Just chuck those pages after last close. And so that will eliminate that, let's call it an Achilles heel of that process. So next, we're going to get into a little more of how PDSE uses storage, and you'll start to see a little more about why that decollect thing was so pernicious. And we're also going to talk about blocked workload. Starting with blocked workload, we need to understand how PDSE and the system really interact with each other in terms of performance. So obviously, yeah, they interact in terms of workload. PDSE is most directly impacted in your system by the CPU resources available, and PDSE is going to be impacting your system, usually overall, in terms of how much storage it's using. So the quick and dirty definition of blocked workload. Blocked workload is something that occurs when low priority tasks are holding resources, let's say a TSO user or some such, it's holding a lock on a PDSE data set. And if you're in a really constrained CPU environment, they may not be getting very much CPU time at all. However, there may be higher priority tasks that are waiting on that low priority tasks resource. If those low priority tasks aren't getting enough CPU, they can't finish their work, and they can't release that resource, we can have high priority workload that's stacked up behind it that may never move along or may move along very slowly as CPU goes ahead and trickles in. And again, this is primarily seen in CPU constrained environments. So if you're running basically pegged at 100% constantly, you could be at risk for this. The symptoms of blocked workload are very similar to a latch hang. You're going to see IGW38A messages, which is our internal monitor's way of saying, hey, resources have been held that are being contended on for longer than a particular interval. Perhaps you need to take a look at this. But unlike a latch hang, we'll see it clear once CPU load decreases. So that means as soon as that CPU frees up a little bit and we can get that resource moving, it'll clear up. If you're in a really marginal case, we'll see it as really slow obtains and releases of latches generally within the PDSE address space. So what are the solutions? Well, we have a couple buttons you can press. The first of these is a IGD-SMS parameter called sysEvent-don't-swap. And that's going to prevent that low priority task from being swapped out even if it's not getting very much CPU. If that task were to get swapped out, it may never get swapped back in, and if it's holding a resource, that resource is never going to get released, which can cause much worse problems. We're also going to do a slight boosting of the service class of the latch holder. We're going to try to get it a little more CPU as much as we can within the constrained environment to make sure that we can at least have the best chance of releasing that resource. In the end, though, the only real solution here is to make sure you have at least a little bit of CPU headroom. CPU is a finite resource, and if you're running pegged at 100%, it's got to go somewhere, and it'll get trickled down to those tasks as available. Sorry? That was back at about 112, I believe. It was 112 or 113. This has been in, the sysevent don't swap has been around for quite a few years now. But again, it's something we want to make sure that everybody has turned on. There's really no downside to turning it on. If you don't have it turned on, please turn it on. It won't hurt anything, and it can only help, especially, again, if you're CPU constrained. In addition, we very recently, and despite the 50,000 Series APAR number here, this is just being released, we've made some serious improvements to the PDSE monitor task, and that's what outputs those 38A messages and tracks contention on PDSE resources. Previously, that task actually took a good amount of CPU itself. And when contention was occurring, it actually sped itself up to better monitor the contention that was going on. That was always the intention, but by speeding itself up, running more often, it actually took more CPU as contention increased, which was not ideal. And what that could result in was essentially a vicious cycle in blocked workload situations. We'd wind up with originally high CPU usage in the system. We'd get blocked workload. That would cause contention in PDSE. Our monitor would then speed itself up, tracking that contention, which would continue to contribute to the high CPU problem. It wasn't major, but again, if you're running at 99.98%, that could be enough to push things and make things basically inoperable. So we've made a huge set of enhancements in OA 50850, essentially in greatly reducing the amount of CPU that monitor task is going to take, and it won't accelerate its CPU usage as contention ramps up, at least not nearly as quickly. Now let's move along to PDSE storage usage. The PDSE storage usage model is what we call a high watermark model. So we will allocate storage as much as we need up to what we call a high watermark. As concurrent utilization decreases, we won't unallocate that storage, but we'll continue to reuse storage underneath that high watermark. And the reason for this being our strategy, effectively, is that PDSE is integral to your system's running. We will not refuse, for instance, a load of a program object by MVS just because somebody's set in a parameter somewhere, should something exist, that I only want to use 1 gig of storage for PDSE. You wouldn't want your system stopping because somebody had set an arbitrarily low storage limit. So effectively, PDSE will take as much storage as it needs to cover the concurrent load. It's one of the last things to go down if you're running low on storage. That storage, of course, its reuse is maintained by our LRU component. But again, the thing to remember here is that your high watermark does not decrease unless you, say, restart the PDSE address space or across IPLs, in which case it starts back at its minimal level. This is a little bit of a diagram as to how it works. The goal, of course, from a performance perspective, is to keep that high watermark from getting too high. We want to prevent having huge numbers of concurrent opens. That's why that decollect issue I talked about a little earlier was such a problem. If you were opening hundreds of thousands of PDSEs all in a very short period of time, your high watermark would spike, but never come back down from there. We would reuse tons of storage under there once all those pages got cleaned out, but our high watermark would remain high, and that was a problem for some customers. Another strategy we can use to prevent this is to make sure that we're using a build-all no-connect when dealing with large PDSE member lists. So if you've got several 100,000 members in your PDSE, use build-all no-connect if at all possible, and to make sure that we use a stow disconnect when we're done processing a member so that that storage can be returned quickly. We finally want to make sure that the LRU is getting a chance to work. I told you the normal timing is about 15 minutes for a page to age out. We can modify that timing a little bit. Again, at the cost of a little more CPU, you can have it go faster. Less CPU, you can have it go slower. However that works out well in your environment, we do want to allow that LRU to work so we can recycle pages and move things along. So here's the levers you can pull for our LRU. Both PDSE and PDSE1 can be, again, controlled independently. And we have the LRU cycles and LRU time parameters. And the way these interact is basically this little equation here. The lifetime of your buffered page is equal to the number of LRU cycles times the LRU time in seconds. So again, default 240 times 15 gives us 15 minutes. We also have a parameter that's slightly misleadingly named the PDSE directory storage parameter. This is by default 2 gigabytes, and I bet almost nobody in this room has this actually set. What this does, a lot of folks have thought that it's a hard limit on storage. It's not. Again, we have no hard limit on PDSE storage usage. What this does is effectively it's a limit at which our LRU gets much more aggressive. So if you have it at the 2 gigabyte default, that means when PDSE hits 2 gigabytes of storage usage, our LRU is going to speed up and go ahead and try to reclaim pages faster. It doesn't mean that requests are going to get denied, and if you're using all of it concurrently, the LRU won't have anything to reuse, and so your storage growth may continue. So while it's a little misleading, it's important to know exactly how that works on your system. Now we're going to move into caching, and this is where we can actually get some speeding up of PDSE performance. When it comes to caching, member data specifically, we have really two options. If you're just dealing with your program objects, we can either have those cached through LLA and VLF or through the PDSE Hyperspace Caching. Now, there are a few differences here. PDSE Hyperspace actually caches all member pages from eligible PDSE datasets. And there are some parameters you have to have set to make things eligible, specifically the MSR value. But again, this can be data or program objects. So if it's important to you to have particular types of data PDSEs, no worries. If it's important to you to have particular data PDSEs cached for quick access, the Hyperspace may be the correct option for you. However, if you're only doing program objects in terms of caching, LLA and VLF really are going to be your best option here. When talking about VLF and LLA, for PDSE program objects, For the best performance, they need to be bound with your fetch options as pack and prime. When you're bound, in page mode, it doesn't actually utilize the benefits of VLF fully. Now, I want to say about 2 years ago, when COBOL 5 first went out, COBOL 5 supports what's called deferred segments. And at the time, it was not a feature of VLF to support program objects with deferred segments. That feature was added in APAR OA 45127. So if you don't have that on, I highly recommend putting that on. Again, it's not terribly new. I assume you all probably have it on. But this will prevent, making sure you have that on will prevent any nasty surprises should you be expecting your PDSE, your newly converted PDSE program objects to go to VLF like your PDS load modules were prior. We're going to talk just a bit more about hyperspace caching. I might have sounded like I was knocking hyperspace caching earlier when talking about program objects, but it is still useful in that it can deal with our data pages also. So hyperspace caching is an optional extension of our buffer management processing. It works essentially the same way as we buffer our index pages, just does it with data pages. This is one of the huge advantages of everything's a 4K page. Doesn't matter to us if it's data or index, it all looks the same. We control this through the hyperspace size parameter, and we also control it with our BMF LRU cycles and LRU time. Again, we're buffering it using the same buffer management processing system that we use for every other part of PDSE, and so it has the same levers to control it. To be cache eligible, a particular PDSE needs to have an MSR value of less than 10. Doesn't matter what it is, so long as it's less than 10. Or that caching has to be requested by LLA when VLF is not available for it, if I remember correctly. Cache data in the hyperspace, again, just like our index data, is valid only so long as the data set is open. Buffer beyond close, however, does also apply to the hyperspace because we're controlling it with the same buffering system or buffer management system. It does apply there. So you have to keep that in mind in terms of your storage usage because, again, rather than just holding on to your general search through a PDSE in terms of the index to go from the root level all the way in the largest PDSE to the leaf level, because it's a B star tree, only takes about 4 page reads. We can do it in 4 page reads. That's a tiny member, possibly. So if you think about it, we could have a 500 megabyte member, and that's a whole lot more pages than a simple page read. So we have to keep in mind what we're using within our buffering. This is just a little more discussion of what I was talking about in terms of COBOL 5, how the hyperspace, VLF, and LA all work together. So now we're going to move on to dataset level performance. We're going to talk about how you're going to use your PDSEs within your Plex in your environment. We're going to talk about what are called pending deletes, how the PDSE index reacts to aging and various other usage. And then we'll get on to very large PDSEs and finally heavily accessed PDSEs, which are kind of the 2 types that are going to have the most impact in your environment. So strengths of PDSEs. The index structure, as I mentioned, it's a B star tree. We can get all the way to the leaf in 4 page reads. It's enormously faster than a PDS, a linear directory search when we're dealing with more than about, I believe it's about 100 members. And our complexity in terms of good old big O notation for the CS majors in the room is far better than a PDS. Our organization is flexible. So again, we don't have gas in PDSEs. We can reuse any area of the data set as needed. And I'll show you that in the graphic in just a second. We have member level sharing between systems. We have caching, so that's going to reduce I/O usage for things that remain open for a while. And of course, we enable the use of program objects, which have way more bells and whistles than load modules and are really what everything's going to be in anyways in the future. So this is actually what a PDSE data set looks like at the disk level. As you notice here, we don't have any chunk that looks particularly like a directory. Our directory pages are actually all scattered throughout the data set. Our member data, is these blue pages, is all scattered in between. So it's a bit like after dinner having ice cream. The ice cream just fills in all the spots in the middle. So we're able to much more efficiently use space within a PDSE. And because everything's just connected by a whole web of pointers, we're able to traverse this very quickly as well. We don't have to go linearly through any indexes. So what are the weaknesses now of PDSEs? There are a lot of strengths, but open, read, and close use cases. If all you're doing is opening, reading a single member, and then closing it again, and doing that over and over and over again, our overhead is higher than a PDS in some of those cases, especially if it's a very small PDSE. We do have to use more storage to support our caching. Okay. We have pending deletes, which we'll discuss in a little bit, and copying a PDSE can be slower than an equivalent PDS, especially for logical copy, because we have a more complex index, and reading essentially linearly through that index can take a little longer if we're not doing search. This all really comes down to, for the Heinlein fans in the room, there ain't no such thing as a free lunch. The key trade that PDSE makes is it consumes CPU and it consumes storage in order to reduce the number of times that we need to go out to the I/O subsystem. We are speeding things up by not having to wait on your disk or your flash or go out to your DS8K. But in order to do that, we need to use storage to hold on to things. We need to use CPU to allow ourselves to search faster. So you've heard pending deletes 2 or 3 times so far. What is it? I promised I'd explain it. Well, what a pending delete is if we have a PDSE data set where somebody has an open connection to a member for read, and then another connection comes in and, for instance, deletes or replaces that member that's already open for read. That may sound a little funny, but this is entirely legal with a PDSE. Remember that when we write to a member, we're actually replacing that member with a new one and unchaining the old version. We can still have folks reading that old version when we unchain it. And we're waiting until that read is done to actually do the deletion and reuse of that, hence the pending delete of that old version of the member. So those pending deletes take up space in the data set. If you still have somebody connected to it, now you essentially have twice the number of members. We have the old member with the reader connected, and we have the new member that we just wrote out. So we have twice the member sitting out there in the data set, even though you're only seeing the new member if you say, did a browse. Once that reader disconnects, we don't get rid of that old pending delete until pending delete cleanup processing occurs. So it can reside in that data set for a good bit of time. Although we've made some improvements, which we'll talk about in a minute, in terms of how we deal with that. But first, how do you know if you have an issue with pending deletes? It used to be that you waited until you saw an IGW 01177T message, which said you were out of space when you were saying, I only had 500 meg worth of members in there. I know I'm not out of space. What is wrong? What you would see is a growth in the utilization percentage for your PDSE if you did, say, ISPF the I information command, but you hadn't added any additional members. And that's because your utilization percentage in the I display takes into account both your current member data and whatever pending delete data is still in the data set. So depending on the number of pending deletes, your 50 members could take up 25%, 50%, or 90% of the usable space in that PDSE, depending on the quantity of pending deletes left behind. Fairly recently, we added a new output parameter to, statistic to IEB PDSE, which is the PDSE validation tool that will actually tell you exactly how many pending deletes you have in your PDSE data set. And what we're looking at here is an I display. And as I mentioned, we have a member count, like normal, and we have a utilization percentage. So this is just an example PDSE that we set up with a bunch of pending deletes in it. So if we run the IEB PDSE validation tool, we now have this pending deletes count down here. In this case, we have 466 of them. So what we actually did with this data set was we opened it, connected to a bunch of members, and then deleted them all and replaced them all. So we have 466 pending deletes. So how do we get rid of them? Well, it used to be that you had only a couple of options. You could IEB copy the data set, in which case the pending deletes get left behind in the old one, only the current members get copied into the new one, your pending deletes are gone, you're good. Or you could activate pending delete processing by making sure that the first and only connection to the data set was an open for output. That turns out was really restrictive because a lot of folks had, for instance, libraries that they never closed. And so trying to get that first and only open to be for output just was not something that was going to work. So with OA 50214, we've enhanced pending delete processing to be way more convenient for you guys. First off, now you don't have to close the data set to do it. This was the major thing. We can deal with PDSE's pending deletes while that data set is still open, still working. Here's how we go ahead and invoke it. We have a parameter here. You can optionally use the no analysis. So if you know the PDSE is good, you just want to get rid of the pending deletes. You don't want to burn any CPU doing a validation. We just put the perform pending delete option on there when you run the IB PDSE tool, and it will go ahead and do exactly what it sounds like, perform pending delete processing. So this is a quick example. In this case, we actually did the analysis. If we didn't do the analysis, you wouldn't see all the statistics here. But it would say that blank number of pending delete members were deleted. And in this case, because we did run the analysis just to confirm that everything went away, we now have 0 pending deletes in that same example PDSE. And here we can see same thing, same information display. We've gone from 97% utilized down to 49% utilized. But notice again that our number of members hasn't changed. This is pretty convenient. We also have a new parameter called PDSE pending delete interval. So nobody really wants to stand around and manually run pending delete processing on your PDSEs or keep track of how close they are to needing it. So now we can also do it automatically. So this will specify an interval in minutes between automatic pending delete processing. So when an open comes in, we will check this parameter and say, hey, has it been more than, say, 15 minutes or whichever since the last pending delete processing occurred? If it has been longer than that interval, we'll go ahead and perform pending delete processing automatically during that open. And pending delete processing is very, very quick to do. We're essentially just marking these things as available for reuse, and we're good to go. There's only a couple caveats to this. First, we want to make sure that the interval time is greater than the time specified by your BMF parameters. So as I said, the default for that is 15 minutes. If you're running pending delete processing less than every 15 minutes on your PDSE datasets, that's way too much, or that PDSE has something very special going on. I'll go ahead and skip that one. So now let's move on to very large PDSE datasets. These are the ones that when you open them, have to search them, are going to have the most impact on your environment. And PDSEs can indeed get very, very, very large. We have a theoretical limitation of, I shouldn't say theoretical, it's a very practical limitation, of about 500,000 members. For good performance, though, your practical limit is probably somewhere around half that, but we do have some customers who are regularly hovering up around the 500,000 mark and things work fine. You just have to remember you have 500,000 members out there, and that can take up a good bit of space. Your performance, of course, is going to be determined by the number of members that are open simultaneously. So if we have to manage 500,000 pages or more, that's going to take up some time. And that's why stow disconnect and build L no connect are really critical when using these data sets. So if you're just going to go connect to every single member, all 500,000 of them, this could take some time in processing. These are also the ones that are most likely to cause spikes in your storage usage. And they're also of the greatest benefit for keeping the index fresh, let's call it. When that index gets very fragmented, especially if you've got a whole lot of members that are being replaced constantly, we can get a little bit of extra space within our indexes, and that can slow down search. Finally, we want to talk about heavily accessed PDSEs. In these cases, this is where hyperspace caching can come in handy. If you have an application that is constantly accessing particular members out of a particular data set, data members I mean, not necessarily program objects, this is a place where hyperspace caching can save you that I/O time and make things a whole lot faster. When we're sharing heavily accessed PDSEs, we need to be sure we're using extended mode. Again, as the number of members goes up, the chances that one of those members is going to be open for output increases. So if we have a really heavily accessed PDSE with a lot of members and we're running normal mode sharing, you're particularly vulnerable to having other systems block that access. And finally, if that PDSE is rarely closed, and this advice actually has kind of become a little outdated with our pending delete interval changes, but still, the number of inserts and deletes that are done should be limited a little bit in order to prevent excess pending deletes from building up quickly. Okay, with that, any questions or comments? This is going to be Jim's favorite slide. Oh.
I know this has been a discussion for a long time. I'm just trying to get a feel for the status of sharing a PDSE between SYSPLEXs.
Okay.
Is that still in a roadmap?
I can't say if it's actually in a roadmap, as in something that we are committed to delivering. It is definitely on everybody's mind. At this point, the roadblock to providing cross-SYSPLEX sharing, true cross-SYSPLEX sharing for PDSE with extended mode is not within PDSE. It is our reliance on XCF for mediating our serialization. Because XCF isn't working across plexes, that's where we're stuck. When that kind of support is delivered, that will be something that we'll be able to take advantage of and then provide cross-plex sharing. There are RFEs out there, at least one I know of. I've seen this over and over. But yeah, the more support we get for that, the more likely it is that the support we need is going to get delivered, and then we can follow up on that. So,
I know phase one was the ability to mark the volume as read only, and that came in 2.3. So I was hoping there was more coming. So, thank you.
yeah.
I know. I put you on the spot.
No worries.
I disagree. It will happen. It will happen. I just don't know if I'll ever see it in my lifetime. Okay?
This is a battle that's being fought above my pay grade.
Being honest. Okay. I'm not saying I disagree. That might not be a great thing to have. Okay, thank you.
Yes.
Any differences with the newer PDSE?
In terms of like version 2 PDSEs, you mean? Yes. So your version 2 PDSEs, especially if they're variably blocked, are going to be much more efficient for variably blocked. Fixed block, though, version 2s are significantly better at keeping their index organized. Version 1s had a tendency where the index blocks, B-star trees work a lot like VSAM KSDS CI, index CIs, where you could wind up with gaps inside them. Version 1 PDSEs were particularly vulnerable to propagating gaps within these index pages. Version 2, now when you do updates, we repack those index nodes so that you're getting a much better, it's not that there aren't still gaps, but there's far smaller, far fewer. And we are constantly repacking them. So with large or heavily used PDSEs, as you add, insert, delete members, version 2s are going to do a much better job of keeping that index tightly packed and keeping it efficient. In terms of performance improvements for your regular fixed block PDSE, a version 2, you might see marginal 1, 2, 3% improvements, but they are there. Does that answer your question? Okay. Anybody else? Any other questions? We are seeing quite a few people playing with it. In terms of like actual applications relying on it, not a whole lot yet, but there is a good bit of activity. There is a freeware application out there called PDSE Gen. It was actually presented at, I want to say it was the last share. I might be confusing myself. Basically giving, it provides a lot of the features and usability and ease of use to PDSE member generations that wasn't included in ISPF at the moment. So if you're interested in it, I really highly recommend checking that out. It's a really cool tool. We're in a phase where people are trying to figure out really good use cases for it. We're seeing like a lot of developers, hey, it's great if I can just, generation off a bunch of, whichever source file I was using, or JCL library, if I made a change to my JCL library, yeah, it's cool if I can go back like 2-3 times in case I mess it up, rather than having to rely on undo or using like a GDG where you have the whole data set. We can do it at the member level. So it's coming, but it's a kind of a specialized use case.
Frank, Lionel, what's his last name? Wrote it with Bill Smith. So yeah, it's a pretty good tool. Yeah.
Yep.
So I think on the CBT. Yeah.
Yeah, and we're actively seeing a lot of requests and usage out of them. They're actively improving the tool. We're seeing a lot of, they're trying to figure out how to make things do all kinds of fancy stuff we didn't intend it to. So that's really cool. We love seeing that. Makes it interesting on level 2, right? Okay, anything else I can answer? There you go, Jim. So yeah, please fill out your evaluations. Let's get to 15,000 evals. MVS storage project, we want to win this, right? Thanks everybody for coming. I really appreciate it.
Because we share. Because we share.